Hello students, in this lecture we will discuss the procedure for drawing Bode plot. Okay, so let's start. Procedure for drawing the Bode plot. So now I hope you got the basic idea about drawing the Bode plot. Now we will see the actual procedure. Okay, here actually I cannot show the actual numerical for drawing that. I will show how to solve the numerical of Bode plot in next class. But you need to remember all these steps for drawing Bode plot. Look at this, consider the transfer function. Here g of s is given. See, transfer function, it always be given in S domain form. Okay, for that you need to rearrange that transfer function in this form so that it will be 1 plus form in numerator as well as 1 plus form in the denominator. You can check that, suppose quadratic equation is there or complex conjugate term is there, then you need to rearrange that quadratic equation also in 1 plus form. So this is important thing for starting the Bode plot procedure. First of all, rearrange the transfer function in standard form. Now see here, s raised to power n is there. Okay. Now in next class we will be solving Bode plot depending on type of the system. Okay. So see, you need to remember the procedure, and for that first of all you will calculate the type of the system from the transfer function. Look at this here, n is nothing but the number of poles at origin. Suppose n is equal to 1, so what you will say? Type, it will be 1. Suppose n is equal to 0, so type of the system it will be 0. No pole at origin. S raised to power 0 means no pole at origin. Okay. So where n is the number of poles at origin, n defines the type of the system. N defines the type of the system. So first of all, from you have to rearrange transfer function in standard form. Then you need to calculate the type of the system. Okay. Now startup steps. Step number 1. Identify the corner frequency. Okay. How you will identify the corner frequency? Look at this here, S term is there. You will put S is equal to j omega, and you can check that here actually for this term I can tell you that this omega n is actually the corner frequency term. Okay. Whereas corner frequency term, it will be there for finite 0 and finite pole. Look at this. Why I am saying the finite? Because 1 plus form is there. Okay. Suppose real zeros and real poles are there. In that case, there will be the corner frequency term. Whereas for the poles at origin or zeros at origin, there will not be corner frequency term. Okay. So you will get a corner frequency term for all these factors. So what you need to do? Identify the corner frequency for each factor. Okay. Then step 2, draw the asymptotic magnitude plot. Okay. First of all, you need to start with a magnitude plot. The slope will change at each corner frequency by plus 20 dB per decade for 0. Okay. In previous lecture I have shown you the magnitude and the phase plot. I told you that magnitude plot is nothing but a asymptotic magnitude plot where we are drawing the line with actual line slope. So for 1 0 it will contribute to line slope of plus 20 dB per decade. For one pole it is contributing to line slope of minus 20 dB per decade. Okay. So for complex conjugate pole, complex conjugate means quadratic equation will be there. Suppose two poles are there. Okay. So it will contribute to line slope of minus 40 dB per decade, whereas for 2 0 it will be plus 40 dB per decade. So it is written that for complex conjugate pole and 0, the slope will change by minus 40 or plus 40 dB per decade. Step 3. In step 3, actually you have to decide from the type of the system. Here I have shown or divided in 3 parts for step 3, 1, 2, 3. Look at this. For type 0, I am underlining. So for type 0 system, draw a line up to first, that is lowest corner frequency. Look at this, from this transfer function you will get number of corner frequency. So how you will rearrange? You will rearrange the corner frequency in ascending order, that is in increasing order. Okay. So what I will consider here for type 0 system, first of all find out the lowest corner frequency. Okay, so draw a line up to lowest corner frequency having 0 dB per decade slope. Please remember, when type of the system is 0, okay, So your first line that you are drawing for magnitude plot, it will be always a line with slope 0 dB per decade. Please remember, means I mean to say that suppose such type of magnitude plot is there, this is log omega, okay, and this is m in dB. So my starting point, it will be always the line with 0 dB per decade, okay. So it may possible that this will be my corner frequency, and at this corner frequency the Bode plot will change, but the initial line slope, it will be always 0 dB per decade, okay. I hope you are getting. This is for type 0 system, okay. So this is fixed rule, okay. Next, for type 1 system, draw a line having minus 20 dB per decade. See, when I am saying type 1, okay, what I will conclude, look at this, type 1 means n is equal to 1. So what you will say, one pole at origin. So one pole is contributing to line slope of minus 20 dB per decade. Here when I am saying that type 0 system is there, so there is no pole at origin. So line slope is 0 dB per decade. But here type 1 system is there. So look at this, line slope is minus 20 dB per decade, okay. So what you need to do, draw a line having slope minus 20 dB per decade up to omega is equal to k. What is this k? K is actually constant term, whatever value of k is there. So you need to put omega is equal to k. So whatever value of k is there, that will be your value of omega. So mark first lowest corner frequency. See, this will be more clear when you will actually draw the Bode plot, okay. But in short, I will tell you, for type 1 systems, when I will draw the magnitude plot, so my first line slope, it will be always minus 20 dB per decade. Look at this. This is actually log omega, then this is magnitude m in dB, okay. So this line is 20, and it may possible that it will change at this corner frequency. Suppose this corner frequency is there, so it may possible that it will change like this. But the starting line slope is always minus 20 dB per decade for type 1. Again, this is fixed rule, please understand. For type 0, starting line slope is 0 dB per decade up to first corner frequency. Here for type 1, starting line slope is minus 20 dB per decade up to first corner frequency. So this may be my first corner frequency omega c1. Now next, for type 2. Type 2 means two poles at origin, n is equal to 2. So two pole will contribute to line slope of minus 40 dB per decade. So look at this, for type 2 system, draw the line having slope minus 40 dB per decade. But what is procedure up to which you will draw minus 40 dB per decade? Up to omega is equal to root k. Okay, here you can check that. Here starting I have shown with 0 dB per decade. Next I have considered omega is equal to k. So actually here k raised to power 1 is there. Okay, here I am writing omega is equal to root k, means omega is equal to k raised to power 1 by 2. Okay, so and so on. So on means for type 3 that value will change. Okay, so and so on, and mark the first corner frequency. So what is conclusion of this? If I will draw the magnitude plot for this third point, so my starting line slope, it will be always minus 40 dB. Okay, so this will be my first corner frequency. So look at this, this is minus 40 dB per decade. Okay, so this is for type 2 system. Again, this is fixed rule, you can check that. When the magnitude plot is with 0 dB, this will be type 0, it is starting with minus 20, so type 1. Suppose it is minus 40, so this is type 2, and so on. For type 3, the starting line slope, it will be minus 60 dB per decade. Okay, I hope you are getting. So the step number 4. Draw a line up to second corner frequency by adding the slope of the next pole or 0 to the previous slope, and so on. Okay, what you need to do? Once you will draw the first line slope, so next line slope you need to add with the previous line slope. Okay, so I will show you with this proper example. Okay, so this is the procedure for drawing. Then see step 5, that is the last step. Calculate phase angle for different values of omega. This is the procedure for phase plot. Okay, calculate the phase angle for different values of omega. Join all the points. Okay, so join all the points. So you know that how to draw the phase plot on the semi-log paper. So last step here I have not written, but I will write step 6. You need to calculate gain margin, phase margin, okay, omega GC, omega PC, and comment on the stability, okay, comment on the stability. So this is important thing. We have already seen how to calculate gain margin, phase margin, omega GC, omega PC, okay. So say student, this is the procedure for drawing the Bode plot, okay. In next class we will solve actual numerical. Thank you students.